Next portion of the presentation, we have Jason Allington, one of our heating experts, that's going to take us through our troubleshooting roadmap using the PID diagrams that we develop and supply with our heaters. So Jason, it's all yours.
All right. Well, we get brought in on existing equipment often for diagnosing, one of two scenarios. The first being it's an existing piece of equipment that over the years, for one reason or another, has stopped working the way it was originally intended for, and the other being that they are looking to increase capacity by either running faster or running new products. And my number one tool for diagnosing what variables I have to work with is the process and instrumentation diagram, or the PNID. And this is something that we develop on all of our new systems during the design and build process. And it's basically a visual representation of every variable and every manual or digital tool that I have to play with within that system. It should show all the automated hardware, control set points and feedback where they are, as well as any manual adjustments that are available within the system. Using this tool allows the operator to step through a system and notice what variables are upstream and downstream of any. It's always extremely important to not only check but also go out and visually inspect. Say I'm changing a damper, I want to visually inspect that in fact that damper is changing. And the importance of this document is that 10 years down the road, when after the machine has been built and operating, this gives me a quick and easy, like I said, it's a roadmap of where changes can be made within that system, or what variables I have to expand the capacity of that system. And it's usually the first thing I print out prior to going out on a new job. Oh, it's not. Oh. So to go through a couple of examples of how I might use this PNID, here's a zoomed in version of the one that I was showing before. And so a common issue that can occur over time is that a box might all of a sudden become positive with positive pressure. And what that means is that you'd be either getting hot air or hot air containing volatiles that is burping out of the entrance or exit slot of that dryer, which is not something that's often liked. So they would be able to see the reading from the PLC on the pressure transmitter that's located in the box. It's also important to go verify that usually there's a gauge on that transmitter, and you can see that it is in fact at a positive pressure. The first step in diagnosing, what is the root cause of that issue would be, in this case, that pressure transmitter feeds back and controls the fresh air that's allowed into the system. Since this is a circle, there's a certain amount of air that needs to be taken out of the system and a certain amount of air that needs to be brought into that system. So if the system is positive, that would mean that the fresh air damper should be closed off completely, because you want to allow less air in. If it is in fact closed off, then I have to look elsewhere for where my issue might be. So I would trace that stream, trace the airstream upstream of it, and I'd say, all right, the next thing on that leg is my exhaust. And I would verify the set point and the physical position of this exhaust damper. If this exhaust damper is all the way open and my exhaust fan is running at capacity, then this isn't yet not the problem. It's trying to get more air and it's not getting it. I would then trace it up further, and now that there are two sets of manual dampers that are controlling the air that's allowed to actually leave the dryer box. Because once again, we're putting in more air into this dryer box than we're pulling out by the manual positions of those. During a commissioning of a dryer, we would manually once and balance the entire system, and we'd usually scribe, mark, and document where they were sitting at, so it'd be easy to identify if these were in fact changed. If they, then my guess would be that we have some sort of and visually inspect and find where that clog would be. Another example of how this might be useful comes from a recent visit that I had, where a customer was looking to increase the overall capacity of their line, which means they are looking to output more energy into the product. So, looking at their PNID, we went and verified that, in order to increase the amount of energy into a product, there's two ways to do it. You can increase the amount of velocity and volume of air that you're feeding to the product, as well as increase the heat within that air by raising the temperature. In that case, it was a quick diagnosis. Their heater was maxed out they had about a 240-degree delta of the air across the heater, as well as their VFD was maxed out. So the system could not be turned up anymore. Using the PNID, the next variable I had to work with was the fresh air coming into the system. Now, this is, of course, ignoring a major rebuild of redesigning the heat system. So without being too intrusive into their operation, we figured out that they had 60-degree air coming into this system. If we were to install an inline heater and raise that 60-degree air up to 160 degrees, that 240-degree delta across their heat source would no longer go from 60 to 300. They'd go from 160 to upper 300s, maybe 400 degrees. So that seems like the process that we're going to go through there. And once again, it's the PNID was a pretty simple one, but the PNID gave us all the variables that we were allowed to work with. On the next slide is another job I was recently out for. This was a case where they had this extremely large system, and there were actually two things that happened simultaneously that made the customer think that the system was not running correctly. They'd shut the system down, and we had done a upgrade to the amount of fresh air that was brought into the system in order to run some new products that had a higher volatile content. During that rebuild period, they also went through and did a deep cleaning of that system. So when they were completely done with the rebuild and done with the cleaning, they went to fire the system back up, and they found that they were unable to run at their previous capacity levels. They were not able to meet web speed and still get the product dry. And they'd spent a lot of time, on their computers, on the PLC, evaluating how the system was being set up, and they were unable to figure out why it wasn't operating correctly. So it was a quick and easy stop in for us. I printed out the PNID. We went out and sat down with the customer. We changed out different, they had already changed out all the pressure transmitters, and we started doing some experiments, raising and lowering velocity. And once again, we were unable to see why the top nozzle velocity was not operating in collusion with the lower velocity. We'd raise the lower velocity, and the top velocity would just stay the same. And after looking at the PNID, we went through and found a very simple fix in that during the cleaning process, somebody had gone through, and right here are some manual dampers that they had closed off in order to clean both sides of the blades. And it was really that simple. The marks were not lining up. They opened up the dampers and the system went right back to how it was originally when it was commissioned.